OpenPOWER Foundation, Hugh Blemmings.
Thank you, and thank you for that warm welcome. It's my pleasure on behalf of the OpenPOWER board and our membership to welcome you all to San Diego, which was actually sunny yesterday, and of course to our OpenPOWER Summit North America this morning. Events like this don't operate in a vacuum or don't run in a vacuum, and we're particularly grateful for the support of our sponsors, our IBM, Samsung and Lladro, our premium sponsors, our Bitware, Inspur, Raptor Computing Systems and SmartDB, who provide a valuable sponsorship to us for the event as well, and our associate sponsors, Everspin, H3, Mellanox, our friends at the OpenCAPI Consortium, Smart Device Technology and Wistron. Without them, these events would not be possible, and we're very grateful for their support. Just a quick snapshot of the OpenPOWER Foundation and membership as we stand, with some 350 members as of this quarter, some 40 different systems in production, many hundreds of hardware and software solutions out in the marketplace today, of which some 150 of them are OpenPOWER ready, certified as well. Within that system space, we really are encompassing everything now from developer workstations all the way to the world's 2 fastest supercomputers. I'm going to just take a moment to introduce Mendy Firmanek, who is offered to wave. Mendy is Director of OpenPOWER Processor Enablement at IBM, but has also recently joined the OpenPOWER Foundation as our president, taking over from Michelle Rankin, who recently retired, and we do thank Michelle for her efforts during her time as president. Without further ado, I shall get us into the first of our keynotes. It's Nikolai Semenov will be presenting this morning. Please join me in welcoming Nikolai from Lladro.
Thank you. So, good morning, everyone. I'm Nikolai Semenov. I'm a product manager at Lladro. We are a platinum member dedicated to delivering OpenPOWER-based solutions to enterprise customers. We have exhibited the Western system many times, but today we have more products to reveal, and I'm going to share what benefits and advantages we see in the power technology or OpenPOWER platform for our enterprise storage products. So the foundation was set up to spur innovation while engineering power-based solutions for data-intensive workloads. But the barebone of this ambitious goal has always been the ecosystem. Our ecosystem of hardware vendors, academia, partners, and ISVs creates a diverse variety of power implementations. Because it's the implementations that bring sustainability and growth. And the core priority of the foundation is to support the development of such a sustainable ecosystem. Through sharing technology, through providing intellectual resources, enabling workgroup cooperation, and hosting events. And then we expect that more power-based solutions would emerge as derivatives of this ecosystem around the foundation. And at the initial phase, the foundation gained a lot of success onboarding a lot of companies, institutions, and individuals. But it's an organic moment to grow to the next maturity level, and it's time to evolve. And at that evolutionary moment, it's extremely important to hunt and search for the new markets, for the new workloads to cover, for the new implementations, for the new niches. And we live in a changing world. The data is exploding. We observe this ongoing data explosion from a variety of different sources. And the volume of it grows faster than our capabilities to handle it, to store, to analyze, for forming valuable insights and high-quality decisions. And that's why the storage market is evolving so fast these days to match the challenges that enterprises face, like rapid digitalization, the necessity to connect and collect everything, and expansion of data privacy and sovereignty laws. We see high demand for robust, scalable, high performance and cost-efficient storage systems. And they must be ready for the workloads of this new era of data that we live in. And as data volumes grow from petabytes to exabytes and beyond, the time it takes to bring the data to compute becomes the essential bottleneck. And so the main focus, it requires rethinking how the storage and compute systems are being designed, and the main focus of efforts in this area has been on reducing the data access latency and improving the rate at which the data can be read from or written to the storage. There have been several attempts to solve this problem. Some of them have failed, some of them are still ongoing, but one way or another, this ongoing transformation gives new perspectives for OpenPOWER members to cooperate in the same field. And this field, we want to bring everyone's attention to is storage. It's a huge market, it's growing enormously, and it has vast communities around both hardware and software components. And it's a great opportunity likewise for the foundation and the members. We are pleased today to share our experience and our success. We are convinced that OpenPOWER technology is perfect for storage. It delivers outstanding performance and great I/O capabilities, including the PCIe Gen 4 in P9 generation. And all of these features come with an affordable price. Also, customers interact with storage systems through high-level interfaces, and therefore they primarily care about capacity, performance, and functional features, some of which are compute-intensive. There is much lower chip architecture competition in this market. So perceiving these advantages of the technology platform for the storage systems, we have been able to prove our views with the real-life scenarios and customers by releasing the new innovative storage platform called Tatlin. It's based on the OpenPOWER architecture, and it has been so competitive and so on time for this ongoing storage market transformation. So in the first year of sales, it allowed us to gain the dominant position on the local storage market, according to IDC Enterprise Tracker. Today, it has reached the 800 petabytes of raw capacity installed in storage systems all over the country and running in production. But this is just the beginning, because we are already very close to reaching and breaking through the milestone of 1 exabyte by end of 2019. So leading by this example, we are encouraging all OpenPOWER members to put their focus towards the storage niche to deliver more of diverse and competitive power-based, not only compute products. And doing this can be of a mutual interest, both for the foundation and the members. By leveraging resources of the foundation, we can make the OpenPOWER the default platform of choice for storage systems, which aligns with the strategy of the foundation. And also, it will help with expanding the use cases and promoting this ecosystem around the OpenPOWER Foundation that we are all eager to develop. So, thank you.
Thanks for that, Nikolai. It's my pleasure next to introduce John Hu from Inspur Power Systems. John is General Manager there. He and his team have brought to market a number of server products based on power for the China and Asia Pacific market, and he's a great friend of our OpenPOWER generally. Please join me in welcoming John.
Thank you. So happy to join the family reunion of OpenPOWER Foundation, and so happy we have more members and more attendees for this summit. And we are very happy to introduce the Inspur Power System to family. The Inspur Power System is the joint venture company between Inspur and the IBM Two Blue company, and I think it is the only company have a power in the company name. So the mission of Inspur Power System is to extend the power footprint in the market, especially in China, and we now have a big power product, not only the power mission critical part, but also the open power part. We're now using in-house design and using JDM model. We inherit from Inspur side. It's a joint development and manufacturing model for the huge customer like BAT in China. Actually, Inspur have a very big market share in China market, especially for the BAT, and we have Inspur have a big product portfolio, and for the IPS Inspur Power System, we can use in their product platform to design a new motherboard. Then we can leverage the market share, and we also leverage the IPs. Which is already very sophisticated for the huge data center market, for the super scale data center. And we also believing in the power system. The open power based design is a more reliable design and a more sophisticated design for the server. I used to design another kind of server, and currently we work with Power and OpenPOWER for a long time to design the system. For the engineering side, we saw the Power more focused on balance the system. Not only the price performance, not only the power efficiency, but also the robustic and the reliability is very key factor for design a power-based and open power-based system. So the philosophy and the guideline for design system is, you can feel the difference. And I think those differences is very critical for customer, especially for the customer for super scale data center. That's giving the I think it is introduce the mature technology into in a faster growth market to allow this market, super scale data center market, can benefit from all the good things in the history. We saw that is very important for our customer, and also our customer feel the difference. Then we also using open ecosystem. That is not only the software part open, but also the hardware part open. We work very closely with OCP, and we also very closely with OpenPOWER Foundation. And in the future, we will open more OpenPOWER based design to the community to allow the family to share the design and to in different regions using the same design, using the same set of open source IP to extend the footprint of the OpenPOWER. We now have a very big product portfolio for the open power system. We show 4 in here. We also have another 2. The first one I want to introduce is in a 4U storage intensive design. Based on our practice, we thought the software-defined storage is a very suitable workload for the OpenPOWER platform, because the PCIe 4.0 for the I/O bandwidth, and also the loss level cache, and also the memory bandwidth, and also the fine design, the macro architecture of RISC. Maybe we should understand the RISC is a very important innovation in the history, and we also in many workloads, especially for the for the storage workloads, we still benefit from the RISC architecture and a fine-tune the design of a macro architecture of the core of the OpenPOWER system. And we found we can using one socket to driven more hard disk driver compared to x86 because the fine design of the CPU, and at the same time we get the similar bandwidth and even better latency. So it's mean we're using 2 CPU to driven 2 times of hard disk driver compared to they're using 4 CPU to driven the same number of the hard disk driver, but we can got the same bandwidth and performance. So that is giving a dramatic benefit for customer. Some telecom carrier in China, China Telecom, and their media company Migu, using our solution to accelerate and get price performance benefits for their media platform. And we now have this one quitted from the x86 platform. Actually, the chassis and the 4U hard disk driver designs used to be in x86 platform, but replaced with OpenPOWER motherboards, the system becoming more powerful. We can have a more bandwidth and a lower latency. The second one is 1U design. I think this is the first 1U design for the OpenPOWER that is in the universal product that you can use for the front end workload, and also used for management of the total system, and also for some some computing density platform need you can put more CPU, more computing power in one rack. The third one is in a 2U design, that is in a general purpose design. This design is in a we see that it's a modular design. Actually, that is in a kind of a transformer. We have many different kind of front end module and the back end module. Actually, that is a 3 front end hard disk driver side module in the front of the chassis, and the back end we have 4 different kind of module. So we combine those different modules with the motherboard together to create 24 different kind of configuration to allow this platform can be suitable for different kind of workload. The third one is in AI dedicated design. We can using this 4U design with 16 T4 or 8 T100 V100 have a more computing power. So for this AI platform, we now have a very interesting POC, and we will win deal with this platform. So the last page I want to introduce, currently I think it is the biggest installation in one of our hyperscale data center customer, one of the BAT in China. Actually, it's T, I think. So for this one, based on the benchmark, first of all, the customer need us to do the customization design. The customer giving us 500 requirements for the BMC modification, and based on the requirements of their data center, and we do that modification based on our BMC design in 4 weeks. They are very satisfied with that. And the second very challenging requirement from customers, they want the per system. The power consumption per system need be lower than 600 watts to be fit into their rack. So that is a very challenging design. We exhausted every design masses to fit that requirement. Finally, we have a 28% performance better compared to the x86 platform, and also for the power consumption, we have 20% less, and using the same level of working load and the same benchmark for the performance. So currently, customers have we have more than 5,000 units to be installed in the data center. That is a big volume installation in hyperscale data center. And the workload is the big data analysis. And we will extend in this customer to the software-defined storage and AI-based workload in this year. So I think that is a very interesting showcase to give us confidence. OpenPOWER definitely can work in the hyperscale data center and carry the modern workloads we have seen in the last several years grows very fast. Thank you very much. Yeah.
Thanks for that, John. That was some very impressive numbers today, indeed, and always very good to have some real world examples. Our next speaker to this audience will need little introduction. Steve Fields is a fellow at IBM and general manager of OpenPOWER. Please join me in welcoming Steve to the stage.
Hi, so I'm Steve Fields, Chief Engineer for Power Systems. So I lead the architecture and design of IBM Power servers, based in Austin, Texas most of the time. Some of you know it's too hot for me to live in Texas right now, so home base for the summer is Portland, Oregon this year, so starting last year actually. So I wanted to spend a few minutes talking about where we've come as an OpenPOWER group over the past 6 years, and we have totally transformed a lot of stuff. I mean, we've completely changed how servers get built, how firmware gets written, how applications get developed, how servers get deployed and managed on our platform, to the point where people can build industry standard servers, use them with industry standard skills. It's an amazing transformation. Many of you in this room have helped with that. So thank you very much for that. In addition, as Tim will tell you more, I mean, we created together the first completely open software firmware stack for server market. It's quite an accomplishment, and I think it's a trend we'll see elsewhere in the world as people understand the value of what we've done together. We've shown the world the value of the I/O subsystem and the performance to be had if you really take hardware accelerators and make them first-class citizens in your servers, attaching them with intelligent buses, and really trying to deliver system value with them, as opposed to what a lot of people have done in the past, which is provide a PCI slot. And of course, we built the two fastest supercomputers in the world together. So we've come a long way. And so now I'm going to shift into a little bit of where we're headed as IBM and as it relates to OpenPOWER. So some of the key focus areas you'll see from us in the near future. So we're going to keep doing more and more on coherent hardware acceleration, as you'd expect. We're making a big transformation in the memory subsystem. So we see AI and in-memory workloads driving a large need for more capacity. Memory costs a lot, even with the price reductions we've all seen this year. So getting the cost in line for high capacity memory is important to us. We're going to be doing more cores in a socket, higher performance networking, higher performance accelerators. We need more bandwidth. And using slow parallel DDR DRAM interfaces coming off of a processor is not a good way to go after a lot more bandwidth. We have on the order of 1,800 pins tied up on our Power 9 processor today just to do 8 channels of DDR4. It's hard for us, it's hard for system designers. If we try to double that, it would be a huge challenge for all of us. So we'll talk about how we're going to change our memory subsystem to get more bandwidth without incurring that pain. And then we're living in a world where there are a lot of new memory technologies in the oven at various memory companies, and we want to get to the point where a variety of memory technologies are exploitable within the server ecosystem. And not just new ones either. I mean, it could be existing technologies that just haven't played in the server world yet. So for example, an LP DDR. Great way to get high bandwidth at low capacity and take the cost of bandwidth down significantly. So we're creating a memory architecture that I'll show you in a minute that enables all that flexibility. And then I won't be talking much about this today, but we also have plans to pretty significantly increase the capability of the open source firmware stack. And corner Todd if you want to ask more about that. So this is our processor roadmap. I think in 32 minutes, this will be shown at Hot Chips by some leaders from our processor design team. So if anyone asks, you heard it first. So we had, going back to the focus areas of hardware acceleration and transforming the memory subsystem, we had some pretty nice plans that we liked a lot in our Power 10 design point. But Power 10's 2021, today's 2019, we have a new CMOS technology to bring online for us for Power 10. And if you've been following the news over the past year or so, you know that we have a new foundry partner that we're bringing online too. So we wanted to make sure we could get that acceleration value, that memory value into the market, kind of decoupled from the bring up of the new technology, the new foundry, and the Power 10 core design. So we added a third element to the Power 9 roadmap using 14 nanometer CMOS. So same cores, caches, technology as the existing Power 9 processors, but making some key transformations in the focus areas that I talked about. So this is a chart that should look very familiar to you. It's almost all the same as what we've shown you for the past few years, couple of years on Power 9. Three key differences. So NVLink, we'll get to the next generation of NVLink to enable ourselves for next generation NVIDIA GPUs. OpenCAPI is going from OpenCAPI 3.0 to OpenCAPI 4.0, and that gives the attached device the ability to cache data from system memory coherently with the processors, as well as posted writes and a few other things. And the guys will go into lots more detail in the technical talks, I'm sure. And then OMI, Open Memory Interface, is the new memory subsystem that we've architected. And I'll show you a little bit about that, and then I think Pete will be up next to show you some more. So in Power 9, and for a long time, we've been doing what we call our buffered memory subsystems or disaggregated memory controllers. So the left side of the page at the top is the Power 9 scale-up processor, where we have an external Centaur memory buffer. These memory buffers are great for giving us high capacity, high bandwidth, and extreme resilience of the memory subsystem. But they burn power, they cost money, they eat up board space. And so to be able to build lower cost, lower power, denser servers that maybe didn't need all the bandwidth and all the resilience, with Power 9 scale out, in 2017 we introduced the direct attached memory subsystem. First time in many years we've done that. And like I said, it's worked out really well for us for what it does. But as we try to take that architecture and scale the bandwidth up significantly, we get major packaging challenges, chip size challenges, board wiring challenges. So where we're going is to a common memory subsystem that takes the concept of a disaggregated memory controller and essentially standardizes it in a way that it can become the memory subsystem for the whole family of future systems. So it will be able to do the high capacity, high bandwidth, highly resilient enterprise things that we do in our high-end IBM servers. It will be able to do standard commodity, industry standard servers at good cost points. And as I hinted before, it will open the door for us using other memory technologies besides DDR DRAM. And the reason for that is the intelligence of the memory controller moves out of the processor into a memory controller that sits on the DIMM, on what's called a differential DIMM or a DDIMM. And so this allows us to break the mold between a processor and a generation of DDR memory. So the simple example of what this will do for us is we'll be able to build systems that start with DDR4 when DDR5 gets cheap enough to use. No processor changes, no motherboard changes required, just plug in DDR5 DIMMs instead of DDR4 DIMMs. I'm not going to go any more into this because I don't want to steal Pete's thunder too much, but so we end up with a chip that looks like this. There's a lot of detail on this page. Much of it is the same as what you've seen before from us on Power 9. So I'm not going to go into a lot of detail. Just want to reiterate that it's a Power 9 chip in every way, except we're increasing the capability of the accelerator attached subsystems, NVLink and OpenCAPI, and we're transforming the memory subsystem. And as I said, all these things lead us into Power 10, so look forward to more great things from us. Thank you.
Thanks, Steve. Thanks, Steve. Our next speaker is Pete Hazen, who's Vice President of Microchip, who looks after a whole range of products that are advancing the data center. So without further ado, Pete, over to you. Thanks very much.
All right. Good morning, everybody. It's great to be here in San Diego with all of you and to be here part of the Power ecosystem. We're very committed and excited about some new capabilities that we're rolling out, as Steve mentioned. So I am responsible for our data center solutions business at Microchip. I think many of you may be familiar with Microchip as a microcontroller company. We have a broad range of products that serve a number of different market segments, including consumer, embedded, automotive. Back in May of 2018, Microchip acquired Microsemi and expanded into aerospace and defense, communications, as well as data center solutions. And within the data center solutions group, we are focused on connecting, managing, and securing the world's information by enabling connectivity solutions across storage, memory, and compute. And at Microchip, we very much believe that the future of the data center is going to rely very heavily on flexible platforms and composable platforms. And so we're directing our energies into those spaces across storage, memory, and compute. So a few comments about what we're currently focused on. We are looking at three distinct market segments: storage infrastructure solutions, endpoint solutions, and memory infrastructure, which I'm going to talk to you about today and follow on to Steve's topic of memory. So first in storage, we have our I/O controllers and our smart RAID solutions. We also have the industry's highest port density SAS expanders, and we are now very much focused on bringing all of those to Gen 4 speeds, including our industry-leading switch tech product line with PCIe switches that enable connectivity between CPUs, GPUs, as well as storage and memory. We also very much focus on enabling NVMe SSDs, which are the fastest and largest growing segment of storage as we look forward. And then finally, we've augmented our product roadmap now with a new focus on memory infrastructure. And a couple weeks ago, we announced a new product called the Smart Memory Controller. And basically, the SMC 1000 has 8 25 gig OMI connectivity that is required for next generation CPUs and SoCs for a variety of high performance computing, including AI and a subset of that in machine learning. So we talked about this at Flash Memory Summit a couple weeks ago. This is a broad industry trend. OpenPOWER is leading in that transition. And this product specifically is designed and optimized to work with the IBM Power 9 Prime processor. If we think about composable memory infrastructure, we see innovation across two vectors: near memory and far memory. And the near memory innovation is really about how do I get more bandwidth to my CPU. As Steve just showed in his roadmap, the processor number of cores has increased from 8 to 12 and now to 24. And we're limited by the number of pins and the real estate that we have available on the package. And so It's really the serialization of memory that's going to enable us to open up that bandwidth to serve the needs of these applications. Second is far memory innovation, and this is really all about pooling memory resources and then sharing those across one or more machines. And that requires a number of capabilities, including fabric capabilities that we're investing in as well. We've been working with a number of partners in the ecosystem that are focused on these new open load store standards, obviously including OpenCAPI, but also the recently announced Compute Express Link, CXL consortium, as well as Gen Z. So there's no doubt this is a very important trend that's going to drive a new market segment around memory infrastructure. If we look at the key trends around latency and bandwidth, this is from an industry paper that is plotting the trends in terms of latency and bandwidth over time. There's really two takeaways to this. When you look at the number of cores that are increasing, the amount of memory bandwidth per core is actually going down. And likewise, the latency per CPU core is going up. And fundamentally, this is driven by the fact that our DRAM buses on our CPUs are limited both in terms of quantity and performance. We can't fit any more pins on the chip, and there are power and performance implications for the current architecture. That leads us to the product that I want to spend a few minutes sharing with you. We call this the Smart Memory Controller SMC1000. It has basically two interfaces, an 8 by 25 gig OMI interface to the processor, and a 72-bit DDR4 3200 interface to our DRAM. And there's really three primary values to this. The first and foremost is the bandwidth. Essentially, we're replacing a 288 DDR4 interface, 288 pin DDR4 interface with an 83 pin OMI interface. So effectively, we're able to quadruple the bandwidth with this solution that is moving the memory interface to a serial interface. And secondly, and Steve touched on this, is media independence. So by moving that controller outside of the CPU, we can now couple the innovation and development of those controller solutions with the new memory, whether it be some form of DRAM, flash, or storage class memory. And then finally, the benefit of lower total cost of solution. You have lower silicon costs in your CPU, you have fewer pins, and you have the ability to drive overall lower costs with less complex packaging. So this product will be available in the market in the form of DDIMMs. There'll be both 1U and 2U. We've been working with our partners at Smart Modular, Samsung Electronics, as well as Micron. And the production availability is aligned with the Power P9 processor. And samples are available today. If you join us out in the foyer later, we have a demonstration over at the Smart Modular booth. And Mr. Jay Bennett will be over there with us and be happy to talk to you more about our new solutions. So please come and join us. We're really excited. I think this very much is the first step in a number of areas related to memory infrastructure. As I mentioned earlier, the Power ecosystem is leading in this space with IBM's processor architecture. Many others are going to follow through some of these other consortiums that I mentioned, first with near memory innovation, followed by more far memory innovation. We also have a technical presentation today at 4:45, so I invite you to join us for that as well. So with that, I'll say thank you for your time and looking forward to working with all of you. Thanks.
Thanks for that, Pete. As you're probably starting to observe, we're drawing a bit of a thread here where we really are starting to see some of the future of computing, not just for OpenPOWER, but across the broader ecosystem. The next speaker is Brian Pan from H3 Platform. Brian will actually be speaking on behalf of H3 and Wistron. Please join me in welcoming him to the stage this morning. Thanks, Brian.
Thanks, Hughes. Good morning. My topic is smarter heterogeneous computing. I will explain how we use the composable GPU solutions to increase the GPU iteration rate and also get your software code higher productivity. This is the AI or HPC workflow. You have a user create different jobs, then submit the jobs to be run as soon as the GPU are available. Then you have a bunch of the GPU server, 4 bay, 6 bay, 8 bays in your data centers. This is a very typical heterogeneous computing scenario. What kind of challenge you will have in the heterogeneous computing environment? In hardware, you need an interconnect with a higher bandwidth and low latency, a suitable protocol to manage your system memory and the device memory. And then, of course, you also need to do your resource optimization for all your jobs. In software side, you have also 3 different challenges. The first challenge would be how to get your code more productivity. Then how to scale your code as GPU increased. Then run your code in different heterogeneous environments. Our solution is the composable GPU solutions. The GPU in PCIe Gen 4 chassis are disaggregated from the server. The GPU could be dynamically allocated to any connected server without shutting down the server or GPU chassis. It means that you can create 2 GPU server, 4 GPU server, 8 GPU server, or 32 GPU server online. Please be noted, all these GPU are connected in PCIe Gen 4 connections. So the latency and the bandwidth is much better than any networking protocol. The server we use is Wistron Power 9 OpenPOWER server with lots of great features. You got 32 DIMM memory, PCIe Gen 4 I/O, and also OpenKB 3.0. The GPU chassis is PCIe Gen 4 based with a 16 GPU slot in it. So let's see what kind of challenge has been addressed in our solutions. For the first and 2, we use the PCIe Gen 4 to address interconnect and memory management. PCIe Gen 4 has 32 GB bandwidth and a sub-micro latency. And the P2P could be run on PCIe Gen 4 protocol. So the first 2 challenges is addressed by the PCIe Gen 4. Our composable GPU solutions could dynamically allocate the GPU to any connected host to increase the GPU utilization rate. Besides that, you can get GPU utilization information, memory utilization information, and the bandwidth information from our chassis. So you can get your code higher productivity by using these 3 informations. Yeah, in summary, what we have provided is that our solutions can dynamically allocate a GPU to provide a hardware flexibility. It's a PCIe Gen 4 based GPU reprovisioning capability. And the GPU utilization rate, memory utilization rate, and the bandwidth could be used to see whether the GPU or storage has been fully utilized by the software core. Of course, you can dynamically add your GPU to see your code can scale or not. With the better utilization and the flexibility, the total cost of ownership of the composable solutions will be better than the GPU server. So we have the demo on the Boots S3. Welcome to check it. And we have another presentation tomorrow morning, 11:30, to explain more how we do it by the GPU composable solutions. Thank you very much.
Thanks for that, Brian. Next speaker will be known to many of you, Tim Pearson, who's the Chief Technology Officer of Raptor Computing Systems. Raptor, of course, are the company behind the Talos 2 and Blackbird developer workstations. Please join me in welcoming Tim to the stage this morning to talk to us about smashing barriers with owner-controlled computing. Please.
I'm Timothy Pearson from Raptor Computing Systems. I'm here to talk about OpenPOWER, owner-controlled computing, and the future. So I'd like to start off with a brief recap of why we chose OpenPOWER now 2-3 years ago. One of the primary reasons for doing this was the fact that we could actually offer secure computing products. We have full source code for all firmware. We have no reliance on external vendor signing keys, so this means that you have full control of your data at all times on these OpenPOWER machines. That's something that most other players in the industry do not offer at this time, and as far as we can tell, do not have plans to. So if you want full control of a system, OpenPOWER is the best way to do that. That implies that the vendor has no way to override your control at any point. These systems are actually compatible with the Raptor FlexVera security technology. That's expected to become available in 2020, and that technology will go ahead and probably revolutionize the actual hardware resilience against both remote and local unauthorized access. These CPUs are very high performance. These are easily the most high performance owner-controlled CPUs on the market today. The ready availability of documentation, of source code, means that you can debug your custom hardware and software solutions rapidly, very precisely. All of these systems ship with the full source code. We provide schematics for our systems to further enable additional hardware module development, system development. Obviously, as has been touched on by a few presentations before, one of Power 9's key strengths right now is its I/O bandwidth. The Power 9 was the first CPU with Generation 4 that enabled us to be the first OEM in the world to ship PCIe Gen 4 systems. The way that IBM has designed the module has allowed that to be a resource that can actually be fully utilized. There's no choke point inside the system where you're not able to really saturate those Gen 4 links. In addition, IBM's shown a great focus on security. If you ever heard about rogue DMA attacks and things like that, these systems were designed in such a way that it's going to be very difficult to execute those. And that's, again, another area where IBM's shown leadership in dealing with the PCI systems. But all that being said, PCIe latency is still going to be a problem, especially when dealing with accelerators. We haven't seen a coherent bus for probably over a decade at this point that is open for everyone to use. So, can we do better than PCIe Gen 4? Yes, we can. It's been touched on earlier. We do have OpenCAPI. This has actually been something that's been in the works for a long time. And is available today on other servers, but these are very high-end machines. It's very difficult to get your hands on the development hardware. What's interesting about OpenCAPI as opposed to some of these other competing solutions is that when it's coupled with a Power CPU, you can again retain those full owner control and open advantages. So, I'd like to announce our new Condor platform. This is a single-socket Lagrange module system. It has 4 standard PCIe Gen slots. It has 8 DDR4 memory slots, and the key feature here is that OpenCAPI memory slot. This is a standard ATX form factor machine. We're expecting to have general availability Q1 2020. And as the case with all of our products, this machine is fully owner-controlled, fully blob-free, ships with schematics. This is ideal if you actually want to go ahead and develop an accelerated solution, if you want to experiment with the idea of coherent memory attach, of literally extending that processor to support your custom workload. In summary, owner-controlled computing is already at a point where it is practical for daily use. We have desktops, obviously the great partners in the OpenPOWER ecosystem. In addition to us, we have servers. Replacement parts are becoming readily available, just as they are with the x86 machines that dominate the industry right now. We have mainstream OpenOS application support at this time. That means that if you use a standard Linux distro, any of the major distros, you're going to see that there's a power port. If you use, for instance, FreeBSD, you're going to see there's a power port there too. To be quite honest, the future's looking great. It's about to get a whole lot better. There's a major announcement that's going to occur tomorrow. And I can't say any more about it right now. But if you're interested in these topics, if you're interested in high-performance owner-controlled computing, if you're interested in developing hardware and software around power, then you definitely want to not miss that announcement tomorrow. I'd like to invite you all to come and visit our booth, S2. We have a couple of demonstration machines running right now. We actually have Unreal Tournament 4, which is one of Epic Games' next up-and-coming flagship game titles running on Power. You can see firsthand how easy it is to switch from your current hardware to Power. And I'd also like to invite you to take a look at our enterprise desktop line. This is something that was announced partially in Europe last year. And we have hardware here now demonstrating that you can use that hardware with Red Hat Enterprise Linux, especially both 7 and 8. So thank you all.
Thanks for that, Tim. I have a few closing remarks, but before we jump into that, would you please join me in thanking all our speakers this morning? They've done a tremendous job. So I have a particularly pleasant couple of duties to perform this morning, hopefully not without too much feedback. A couple of awards. Last year we had our inaugural OpenPOWER All-Star Award. Last year it was presented to Jeff Brown, who was the Technical Steering Committee Chair for many, many years of the Foundation. The awards are, or the award recipients, I guess more precisely, are determined and deliberated on by the board. And this year it was thought that it would actually make sense to present two of them. So our first OpenPOWER All-Star Award for this year goes to someone who's worked tirelessly to keep the OpenPOWER website and all infrastructure that goes with it up to date, running and current, and recently oversaw a fairly major revamp of the entire website. So would you please join me in congratulating Scott Schultz, our first All-Star Award. Scott, if you come up for a moment, please. We're going to save you from saying a few words, but thanks so much for all your support, sir. We didn't actually, yes, I was. Thanks so much, Scott. Appreciate it. Please thank Scott one more time. I think I mentioned it, but the two recipients aren't actually aware that this was on the cards for them. It took a little bit of subterfuge to ensure they'd actually be here, but it seems to have panned out, so that's good. Our next recipient is a tireless promoter of OpenPOWER worldwide, spends more time on aircrafts than it feels like I have hot breakfast. He's promoted OpenPOWER in academic circles, in commercial circles, and also leads our academic discussion group. So please, without any further ado, please join me in congratulating Ganesh Narayansamy for all his kind effort and all his efforts.
Thank you.
Thanks, Ganesh. Thanks very much. Thanks again. Please. Which pretty much leaves us for a couple of last logistics. We have morning tea out in the hallway very shortly. Our technical sessions will commence at 10:40 this morning, and we have an evening social event starting just around 6 o'clock this evening that's sponsored by Samsung. And with that, we'll close this morning's proceedings. Thank you all again for your attention. Do appreciate it.